in case of phenols, are connected to benzene ring, aromatic ring. So they are, this is why they are phenols. The name phenol is the name for both as a specific compound, hydroxybenzene, which is just one aromatic ring and hydroxyl group. This is phenol, right? But also this is the family of compounds. So those which have this hydroxyl group connected to benzene ring, they are called phenols. Okay. Well, phenols are usually named with the ending phenol rather than with benzene. So since where there is hydroxyl group, it is ended as phenol. For example, if we have compound like this, where we have one chlorine substitution and the hydroxyl group, it's going to be O chlorophenol. Why it's O? Because we have ortho position. So 1, 2, right? I'm sorry, 1, 2. Okay, so we have ortho position. So this is why O chlorophenol and the rest is phenol, right? Or it's going to be P methyl phenol because we have at para position substitution of methyl group, we have at para position with regards to OH. Okay, so well, phenols are water soluble. Most of them are water soluble to some degree and have higher melting and boiling point than similarly substituted alkene benzene because of this hydroxyl group. So they can make some hydrogen bondings. Because of that, they have higher boiling point. Yeah, so rather than similar substituted methyl or some kind of alkyl benzenes, okay? Well, acidity and of phenols and alcohol. So when alcohol dissociates, so this is the alcohol, right? So when alcohol dissociates, it breaks like here. So you can see that it produces hydrogen ion, eventually hydronium ion, and the rest of as an anion. Okay, so it does dissociates, giving away hydrogen ion. Because of that, when you dissolve alcohol in water, it has a little bit acidic reaction. So it has it makes water a little bit acidic. The same about phenol. So the phenol dissociation is the same. So it breaks down over here. So the hydrogen is separated and then it makes this hydronium ion and the rest is over here. Well, this is phenols as antioxidants. It's well known that phenols are antioxidants. You can see it on some written labels. There is BHT and BHA, so it's about phenols. In general, phenols are antioxidants. Now let's just talk about ethers. Okay, the ethers differ a little bit from, in terms of structure, from the organic molecules we studied, but it's not really complicated. Only thing is that there is an oxygen in between of two carbohydrates, okay? Some kind of carbohydrate groups. So the connection between these two goes through the oxygen. And if we have something like that, this is going to be ether. So this particular one is dimethyl ether. The boiling point is minus 24.5. So basically at room temperature, it's gas. The other one is ethyl methyl ether. So this is ethyl. This is methyl. And it's connected through the oxygen. It's going to be ethyl methyl ether. Boiling point is also very low. It's also gas at room temperature. And diethyl ether, it's not really gas at room temperature because the boiling point, it becomes, see how big difference is between these two. So substitution of methyl with ethyl, so it makes the change of properties pretty much. Yeah, so ethers do not have this hydroxyl group, right? So they have oxygen, but they do not have hydroxyl group. So compared to alcohols, they are not really well soluble. So small ethers can't be dissolved in water, but compared to alcohols, they are really poor soluble in water than alcohols. So because of this issue, they do not have this hydroxyl group. Well, ethers are alkane-like because mostly it's carbohydrates, right? But ethers easily react with oxygen, and the simple ethers are highly flammable. Okay, so we should not keep it in air because many ethers form explosive peroxides, which contains oxygen-oxygen bonds, and ethers must be handled with care. This is some derivatives like from ethers. For example, diethyl ether has now been replaced by safer, less flammable anesthetics because diethyl ether was used as anesthetics. It was not easy to control it because you need to control, right, the patient under anesthesia. You need to control it, but it's using diethyl ether. It was not that easy to control, so it was substituted by isoflurane, this one. So this is used as anesthetics right now. This is just some information about ethers and living environment around us. This is some history also, by the way. It's very important point in history of medicine, especially dentistry. You guys are future dentists, right? You should know that William Morton in 1846 demonstrated ether-induced anesthesia during dental surgery. And it is marked as the one of the most important medical breakthrough of all time. Because before that, all surgery had been carried out with the patient fully conscious. You can imagine, right, how difficult it was for the patient. And then they will introduce this ether as an anesthesia. Also, it was chloroform introduced in 1853, again with after Morton's work, and so on. Then there was started this history of anesthesia. All right. This is just styles. Just for your information, we will not be focusing on this very much. This is thiols and disulfides. By the way, usually thiols are stinky. They stink. And you know this animal skunk? Skunk, this animal, it's very stinky animal. So it releases some compound with thiol, and it basically threatens the predators by releasing this terrible smell, which is basically comes from thiol. These rotten eggs, stuff like this, all these things are from thiols. Also, by the way, thiols and sulfides, right? We talked about thiols and sulfides. Interesting thing is that cysteine, for example, which contains thiol, this is just for information, just to know about this. This is amino acid, one of the amino acids. It contains thiol, and this is in charge that we have curly hair. If somebody has curly hair, like more than, so it means that they have more this cysteine in hair. And these sulfides, sulfur atoms, keep strands of hair together, and they make it curly. So it means that chemistry can curl your hair. A permanent wave results when disulfide bridges are formed between SH groups in hair protein molecules. Okay. Basically, this is it for phenols and alcohols and so on. From this part, you need to know about benzene, aromatic compounds, about alcohols. Yeah, by the way, I want you to remember toluene, phenol, aniline. So you will need to know about Benzene, aromatic compound, as I said. You need to know also about alcohols. Okay, and phenols. Oh yeah, and ethers. So what I want you to remember how they look like, okay? What is the structure of ether, what is the structure of phenol, and what is the structure of alcohol and benzene. Do you guys have questions in this part? No.
No, like everything.
All right, so you might think that it's too much, but if you just follow it, it's not really difficult because we do not go any complicated organic chemistry, just very simple structures, very basic. And just to follow me, it will not be very difficult. You're supposed to have this course, by the way, before coming to the university. Usually schools are providing these courses. Just we are going to refresh the knowledge and also try to connect it to the chemistry, okay? Where they are used, why they are used, and so on. All right, so let's just talk about amines. I'll explain what does it amine look like. You should think about ammonia. You remember we studied ammonia, NH3. It's very resembling ammonia, these amines, but only difference is that instead of one hydrogen here, there is some kind of organic group. All right, so there might be organic group instead of another hydrogen, right? So two organic groups, or even third hydrogen, right? Three organic groups. So this is difference between ammonia and amines. But again, if you think about ammonia, the very similar thing is amine. So you can see here that, so this is ammonia, it's nitrogen, this is hydrogen, and if you look here, they're the same thing. This is nitrogen, and it's connected to some kind of organic, three organic groups, okay? Sorry about this one. Okay, so well, the same thing is, you remember we also studied ammonium ion, so NH4. If you remember, we, especially when we did some pH stuff, Henderson-Hasselbalch equation, if you remember, there were some questions about this. So also the same thing in organic chemistry, amines can make quaternary ammonium ion, like quaternary ammonium ion. It can be also like this one. See, so this is organic group, organic group, organic group, organic group, and it makes nitrogen plus. So it's the same as NH4 plus. But instead of hydrogens, there is a organic group. By the way, we'll talk about carboxylic acid, but amine group is a part of amino acid. So in amino acid, we have carboxylic group and amine group. Okay. So, all right. So now let's just name amines. The naming is also very similar to other organic compounds. Like, so we have amine, and there is connection of organic group, so it's going to be ethylamine. Okay, so this is isopropyl, so this is isopropylamine. So this is cyclohexene, so this is going to be cyclohexylamine. Okay, so this one is dipropylamine because this is propyl, this is propyl, this is dipropylamine, and because in the middle we have this one, right? So this one is 3-ethylamine because this is ethyl, ethyl, ethyl. So we have 3-ethylamine. If we have different substitutions, so look at here. So this is ethyl, this is propyl. So if we have two different substitutions, then we name the parent compound based on the longer substitution. So this is longer, right? Because propyl is longer than ethyl. This is going to be the parent name, but on top of that, we will have a name of substitution like this one, N-ethyl propylamine. So N-ethyl comes from here. So why it's N? Because this ethyl is connected to nitrogen, okay? So this is what it indicates, N-ethyl propylamine, because this is propyl. The same thing here, look, we have two substitutions, both of them methyls, and then we have propyl. So it's going to be N, because this is connected to N, and this is connected to nitrogen as well. So both of them are connected to nitrogen. This is why for both of them, N. Then D, because we have two of them, one and the other one. So D, methyl, because both of them are methyl, propylamine. Okay. Everything is logical here. Just you need to remember it. So now there is no calculation in this part of chemistry, right? Which you didn't like, but now you're just memorizing. So you just need to memorize. Oh, I'll not stop here. It's about like smell of some amines, and this is about cadaver dogs, which can smell some rotten meat. Properties of amine. So primary and secondary amine. So what is the primary and secondary amine? So when you have N, H, and one organic group, some kind of organic group, it's going to be primary amine. If you have two of them, one group, another group, and this is H, this is secondary amine. And if you have all of them organic groups, 1, 2, 3, oh, then it's tertiary amine. So the primary and secondary can hydrogen bond because they have hydrogen. So they can do hydrogen bonding. And higher boiling, so because of that, they have higher boiling point than alkanes because they do hydrogen bonding. Remember that if the compound does hydrogen bonding, it means that they can have higher boiling point. Tertiary amines are lower boiling point than secondary amines or primary amines because they do not have any hydrogen in there. Simplest amines are gases, other common amines are liquids. Volatile amines have unpleasant odor. For example, as I said, cadaver, rotten fish and rotten meat, smell comes from amines. So simple amines are water soluble because hydrogen bonding with water, and amines are weak Bronsted bases because they can accept hydrogen proton, hydrogen ion. Many amines are physiologically active and many are toxic. Well, this is heterocyclic nitrogen compounds. I'll skip this one. Also, I'll skip this because you can just read it yourself. This is about Nobel. Very interesting story about Alfred Nobel, who is a founder of a Nobel Prize. Okay, this is also about NO, how it, by the way, I really recommend to read it because there is a very important role for NO. For example, NO, nitric oxide, it helps to control vascular tone, allowing the arteries to relax and stay clear. Compounds that release NO are being considered for inhibition of the growth of cancerous cells, protection of vessel walls after surgery, promotion of wound healing, and killing parasites. So what is interesting that NO is considered as very important biological molecule. As I said, as I read here, so it's very important for the functioning of organisms. At the same time, it's pollutant. If it goes out to the air, it's considered as pollutant. Also, these amines are amine salts. So, as I said, amine is when you have three organic group, right? For example, but if you have something else, for example, Cl or whatever, I'm sorry, if you have some more organic group, then it's going to be plus, and if you have Cl minus, then it's salt. So this kind of salt, for example, benzalkonium chloride is considered as an antiseptic and disinfectant. And this is also used as a surgical scrub. So you can see that it's very wide application of amines. All right, so this is amine salt. I'll skip this one as well because there is information that, you know, something is used in perfume and, you know, all kind of stories about some compounds. Do you guys have questions about amines? Okay, so then, all right, so then let's just go to carboxylic acid. You know, I want you to also have idea about carboxylic acid because next year you go to and study biochemistry next semester. So you will study a lot of amino acids and you need to have understanding what is this amino acid, okay? So so we studied like simple acids, inorganic acids, but let's just go to organic acids. Okay, you guys have heard about fatty acids, right? So what is organic acid? Organic acid is pretty much determined by carboxylic as carboxylic acids, and they have OH group bounded to the carbonyl carbon atom. So this is carbonyl carbon atom, and this is carbonyl carbon atom. So this is carbonyl group when you have carbon double bond oxygen. And if to this group there is also OH, so then this is considered as carboxylic group, and this carboxyl or carboxylic group determines the properties of acid, of carboxylic acid. So there is a carboxyl group. So this is the functional carboxyl group, which is COOH, right? The same as here, COOH. So if you have two carboxylic groups, right? So connected to some kind of organic group right over here. So it can be R, some kind of R prime. So you can see that there is a hydrogen bonds created between hydrogen and oxygen, So the carboxylic acids of low molecular weight, so they pair up making hydrogen bonds. And some of so small acids are soluble in water because of making these carboxylic groups. Now this is, let me see here. I'll go to this one first, and then if we have time, I'll come back. So now let's just see how to name carboxylic acids. Okay. So carboxylic acids are named according EUPAC system by replacing E of the corresponding alkane with OIC acid. That's the whole story. Say if you have propane, say you have propane, right? Propane. Corresponding carboxylic acid is going to be propionic acid. You just change E by OIC and then add acid. That's the whole story. So why it's propionic acid? Because you have 1, 2, 3 carbons. You have carboxylic group also. So it's going to be propionic acid. Now how to number the carboxylic acid and have some exact naming if you have substitution. You start numbering from the carbon which is related to the oxygen through the double bonds. So that's the first carbon you start numbering. So you need to find this functional group in the molecule first and then start numbering. So it's going to be 1, 2, 3, 4, right? Now we see that there is a substitution as methyl group coming to third one. So then we say 3-methyl butanoic acid. Why is butanoic? Because we have 1, 2, 3, 4, which is butane. So we say that if it is connected to the carboxylic group, then it's going to be butanoic acid. On top of that, we have methyl group, and it's going to be methyl butanoic acid. Okay. This one, yeah.
Doctor, can you repeat from the page?
Okay, so let me just erase this one. Okay, so how to number, first of all, carbons in carbonic acid. We start numbering from the carbon, which is related to the oxygen with double bonds. So we are numbering the carbon of carbonyl group. Okay, so we start numbering from here. So this is going to be 1. Okay, and the rest one is going to be 2, 3, 4, right? So because we have 4 carbons in carboxylic acid, because this is carboxylic acid, right? Because we have this group. So because of that, this is butanoic acid, because we have 4 carbons in there, right? It comes from butane, changing ending E by OIC acid. So it's going to be butanoic acid, but also we have substitution, right? So substitution comes on the 3rd carbon, because according to this numbering 1, 2, 3, 4, it comes to the 3rd carbon. So because of that, this is 3-methyl butanoic acid.
Doctor, just we add EOIC.
Yes, instead of E, you changed E by OIC. So it's going to be propionic or butanoic acid. In this case, it's also propionic acid, right? So here the same thing, you start numbering here 1, 2, 3. And because on the 3rd one, there is a hydroxyl group over here. I'm sorry, on the 2nd one, there is a hydroxyl group. So it's going to be 2-hydroxy propionic acid. Okay, is that clear?
Doctor, there is no need to write the carbon atom number, yeah? For example, in the second one, we can say 3-methyl 1-butanoic acid.
Okay, so for this one, no, because it's always like comes to this carbon, always. So it's always 1 butanoic acid, it's always 1 propionic acid.
Yeah, if we have, or is it possible to have 2 carboxylic acid in one structure?
There is, but it's different story, so it's complicated. We will not be going to that point. So we will not be studying this kind of thing. But sometimes there is 2 carboxyl groups in acids, and then there is a complicated names, and it's not that simple as we are talking right now. Okay, but yes, you do not need to write number in front of, say, butanoic acid. You don't need to do this. Okay.
Okay, thank you.
All right, so yes, you know, there are some carboxylic acids which have historic names, you know, because those carboxylic acids were one of the first which we are identified, and they were like named like historically. For example, formic acid, if you have heard about formic acid, or for example, acetic acid. Have you heard about acetic acid, right? I believe we studied it sometime before, as when we did about buffer solution, we have acetic acid, acetate. So acetic acid is named like historically like that. So if we have lack of hydrogen, right? So we do not have hydrogen here, right? So then it's going to be acetyl group. Sometimes, you know, we need to understand, and if there is no this hydrogen, it's acetyl group. There are some common physical properties of some carboxylic acids, some complicated, as you see here, we have 2 carboxyl groups, even 3, 1, 2, 3. See, 3 carboxyl groups. So this is citric acid. So then the names are really, you know, this is considered as a class of subclass of carboxylic acid, and names are complicated. So we will not be studying this kind of thing. This is citric acid, which is in citrus, you know, citrus or citric acid. You know, citrus like lemons, like oranges and mandarins. So they have this kind of acid. Acetic acid, I was talking about acetic acid. This is a vinegar. You guys know vinegar, right? So that's the vinegar is. This is vinegar, okay? Or stearic acid, it's like animal fat. This is very, very, very big acid. See, there is a 16 of these ethylene groups, okay? This is very huge acid. It's just huge acid. It is from animal fat. And there are some properties of carboxylic acid. For example, formic acid, as I was saying, formica, it comes from ant. You know, the insect ant. So it releases this formic acid, and it comes from, the name comes from there. I talked about amino acids. We are not going to study amino acids, but you need to understand that in amino acids, we have amine group and carboxylic group. Both of them must be there, and some kind of, you know, carbohydrate. This is amino acid. Okay. I want you to, now let's just go back. I told you that I'll give you some nomenclature information. Now let's just go back. So what we can derive from carboxylic acid. So this is carboxylic acid, right? So what we can derive from here, we can substitute, for example, this H by different carbohydrate. For example, this one. This one. Then if we do so, it's going to be ester. Ester. Okay. So we can substitute the whole one, like OH, by amine group, the whole one. Okay. Don't be confused with amino acids. So now you see we have amine group, but we do not have COOH group. So we do not have carboxyl group anymore. What we have, this is carbonyl part over here. And we have some kind of hydrocarbon, okay, and also amine group. So this is amide. Have you heard about amide? I believe you did, right? Okay, so I just want you to understand some reactions of carboxylic acid, ester amide formation. So this is esterification reaction. It's called esterification reaction. It's not difficult at all. Just follow me. So this is carboxylic acid over here. And this is alcohol. Right? That's the same thing as CH3OH, for example. It's just rewritten in a different way. Like if you write it like this way, it's HOCH3. Just it's a rewritten different way. Under the catalyst, what is happening that this OH and this hydrogen are connected, and you are obtaining water. And whatever is left, it's ester. Okay, this is why it's called esterification reaction. For example, this is a particular example when we have butanoic acid plus ethanol, we can make ethyl butanoate. This is, by the way, in pineapple oil. This compound is in pineapple oil. You can see what is the variety of organic compounds. You can see it everywhere around. Another reaction is amide formation. So what is happening here? We have carboxylic acid, we have amine, and OH and H from amine are connected. I have less than 1 minute left, but please come back after this is done. And under the catalyst, we are producing water. So from here, we are producing water and amine. Okay,
Can you repeat it, Doctor?
the last one.
Yes, the last one.
All right, so we have
And
the-
example, Doctor, if you can.
yeah, so you want example?
Yes.
Yeah, it can be anything. So let's say like this way, you have acetic acid, for example, CH3, C, O, OH. O, and I'll connect H like this way. Okay, 1 second, I'll just delete this.